In real life, linear algebra is done numerically, not by pencil paper, but the actual computations are done by computer algorithms. Now, those types of algorithms are prone to errors. There's always an error introduced when you convert a problem into a numerical form to be solved by a computer. So numerical analysts prefer matrix factorizations that have orthogonal matrices in them, just like in this QR. That Q is an orthogonal matrix. Well, why do they care about orthogonal matrices? Or if your vector x has some error built into it, your computed solution, multiplying it by an orthogonal matrix will not change the length. It will not amplify the error that's already there. So there is no error amplification. That's why orthogonal matrices are preferred. So the goal really in linear algebra, whether you realize it or not, is to find matrix factorizations using orthogonal matrices. Now we are going to start in this section with diagonalization. We know that we've got the ability to write some matrices in this form, PDP inverse. It depends on whether or not the matrix has enough eigenvectors. Can an orthogonal set of eigenvectors for our matrix A? Because if we can, then we can take this matrix, and remember that we put the eigenvectors in this matrix P, and if we have an n by n matrix, we need a basis for Rn, but if we can find it, we will put them all in this matrix here, and we'll call it Q instead, and we'll have Q, D, Q inverse. But one of the other advantages of this is that, again, the inverse of an orthogonal matrix is just its transpose. So there's even less error involved there. You don't need to find the inverse. You don't want to waste computational effort finding it. All you do is transpose your matrix. So this is our goal. Can we find a matrix factorization with this? And we're going to call this an orthogonal diagonalization. Now, just as a little example, right, we can take something, simple 2 by 2 matrix, and let's talk about whether or not this matrix has a diagonalization. So we would have to first of all talk about its eigenvectors. So we need this characteristic polynomial. If you sit there and compute this, what you would eventually find is that you'll get lambda plus 3, lambda minus 2 is 0, so you can pause the video and try that for yourself. This matrix has two eigenvalues, 2 and negative 3. And because we know that the eigenvalues are distinct, we are going to have enough basis vectors here. So if we find the eigenvectors, all we do is we plug this in and we try to compute the systems that we need. So A minus 2i into V is 0. If you plug all of this in, it will very nicely work out to a result that's easy to digest. And what you'll find is that your first eigenvector here is going to be 2, 1. Your second eigenvector, you'd have to solve A plus 3i into V is 0. You plug everything in there, you'll get another very easy system, 2, 1, 0, 0, 0, 0. And you'll find that your second eigenvector is also very easy, 1, negative 2. So yes, this matrix A is diagonalizable. That means you can find a basis of eigenvectors in terms for R2. But check this out. If I were to take V1 dotted with V2, here's what I'd get. 2, 1 dotted with 1, negative 2. It's 0. So what does that tell you? We have an orthogonal set of eigenvectors. Yay! That was a nice coincidence, right? V1 and V2. But we want to go one step further. Now we want an orthonormal set. So what we would have to do is take these eigenvectors and normalize them, divide by their length. So we'd have 1 over root 5, 2, 1. U2 would be, again, 1 over root 5, 1, negative 2. And so our orthonormal set of eigenvectors here, U1, U2. Now, just again, to impress upon you why this is good, normally if you want to find an orthogonal set, you have to do Gram-Schmidt. But we didn't have to do that here. It was all built into our matrix. So what we have now found is that if we let Q equal U1, U2, a matrix with these two columns, its inverse is just going to be the transpose. So we have now found a diagonalization. We can take our two eigenvalues, put them in like this, and we have now found an orthogonal diagonalization of this matrix. So I'm just going to abbreviate it OD. Are there conditions that guarantee that a matrix has an orthogonal diagonalization? Where should we start? Well, here's a really easy way. We'll kind of start in reverse. So suppose A does have an orthogonal diagonalization. What can we say about A? Well, here's a nice easy one. If I were to take the transpose of a matrix with an orthogonal diagonalization, remember that the transpose of a product is the product of transposes in reverse order. The transpose of a transpose, you're just basically swapping rows and columns and then doing it again. So you'll get Q dt QT. Now, if you've got a diagonal matrix, remember you only have non-zero values down the diagonal. Taking its transpose won't make a difference. You'll still get the same matrix. So guess what? It's equal to the original matrix. So if A has an orthogonal diagonalization, then A is equal to A transpose. That type of matrix is special. This is called a symmetric matrix. So if a matrix is equal to its transpose, it's called a symmetric matrix. So we've kind of found the opposite of what we want. We've said that if you are going to have a orthogonal diagonalization, you have to be symmetric. But I want to know if the other way it goes, right? If I'm symmetric, will I always get an orthogonal diagonalization? So I don't quite have the story. Now, if you have a symmetric matrix, the word symmetric sort of implies some symmetry, right? Well, here's the symmetry that we're talking about. In a symmetric matrix, you take your diagonal, and then all the off-diagonal elements are just flip-flopped, right? It's literally a reflection across that main diagonal. So if I were to take something that was bigger, so like this, and let's say I'll put a negative and a negative. Again, if I go down the diagonal, I have to have a reflection. So that negative can't be there to be symmetric. It would have to be here. There's a negative. That would be a symmetric matrix there. And then these elements would have to be the same, and these elements would have to be the same. So it's literally a geometric flip. What else can I say about a matrix where A is equal to AT? Does it always have an orthogonal diagonalization? That's ultimately my goal. That's what I want to know. So I'm going to partially piece this story together. Okay. So here are some other properties. So let's suppose that A is equal to AT, it's symmetric, and that it has distinct real eigenvalues. So let's say that it has a lambda 1 that produces one eigenvector and a lambda 2 that produces another eigenvector. Now, there's no guarantee that a symmetric matrix is going to have eigenvalues or that it's going to have more than one, but just for the moment, we will say that it does. Okay? If it has distinct eigenvalues, I don't know anything about the dimension either. Could be one-dimensional, has to be at least one-dimensional, but it might be bigger. So if I just take any eigenvector from that eigenspace, I want to talk about them. Let's discuss the orientation of this V1 and V2. As I said here, lambda 1 V1 dot V2. I kind of went the other way. I'm sorry here. I should pull this back in. And you'll say, well, why did you go that way? Well, here's why. Okay. I am somehow trying to bring in symmetry. And I'm trying to talk about orientation of these vectors. Orientation's through dot product, and the only way to bring the matrix in is by talking about eigenvalues. So if I can put that lambda beside the V1, that means I'm allowed to bring in, by definition of an eigenvector, I'm allowed to bring in that a V1. Okay? Now, by definition of dot product, I could write this as a V1 transpose times V2. And you see, I'm trying to bring in these properties, symmetry of the matrix, orientation through dot product. V1 transpose AT transpose V2. And this now is the important part. Because the matrix is symmetric, I can essentially get rid of that A transpose. And I'll have V1 transpose A V2. I can put a bracket there. And I know that A V2 is just lambda 2 V2. I've sneakily shifted the matrix from V1 onto V2. This is by definition of dot product, just V1 dotted with V2 lambda 2. And by dot product properties, I get lambda 2. I can take out the constant V1 dot V2. So there's a big string of things that have happened. I started with lambda 1, V1 dot V2, and I worked my way down through all of these properties, right? Eigenvector, definition, dot product, definition in terms of transpose, and I just worked my way through. So here's what I found. Lambda 1 V1 dotted with V2 is equal to lambda 2 V1 dotted with V2. If I organize this by putting a right-hand side of 0, here's what I've got. This stuff is equal to 0. Well, the only way a product of two things can be 0 is if one of them is 0, the other one is. But I already know that the lambdas are distinct, so this thing cannot be 0. And the only option then is that V1 dotted with V2 is equal to 0. And if their dot product is 0, they are orthogonal. And that's a really important point. Eigenvectors from each eigenspace are orthogonal. So if my matrix is symmetric, then eigenvectors from each eigenspace are orthogonal. And now that's important, right? Does a matrix that's symmetric have eigenvalues, right? Does it have one? Does it have more than one? I can prove another result. Now, I'm not going to go through this proof because it really needs to talk a little bit more about machinery with complex numbers and dot product. And we just haven't gone through that yet. But you can prove this using complex numbers and dot products. And basically the point of the story is that if your matrix is symmetric, then A always has real lambdas, and it will have n of them, counting multiplicities. So you could have a repeated lambda. This final result is something called the spectral theorem. The word spectral talks about spectrum. Spectrum is kind of a range of things, and in this context, it's called spectral because we're talking about the spectrum of eigenvalues that a matrix has. This is all to do with a matrix A that's square, and we are going to assume that it's symmetric. So let A be a symmetric matrix. Then you get the following things. A has n real eigenvalues if you count multiplicities. B, the dimension of each eigenspace is equal to the multiplicity of the lambda. So if you have a twice repeated lambda, it's going to have a dimension of 2 for its eigenspace. The one we did prove is that each one of these E lambdas is mutually orthogonal. So you can see we're kind of building to this final result. A is orthogonally diagonalizable. So we showed that if you are orthogonally diagonalizable, you had to be symmetric. Well, now we've got the flip side of the coin. If you are symmetric, A equals AT, then you must have an orthogonal diagonalization.